Okay, we're going to start section 7.4 here, which is called partial fractions. There's two important integrals to know first for this section that are going to come up a lot, okay? And that's these two integrals right here. So if you integrate 1 divided by ax plus b, that would be just 1 over a times the ln of the absolute value of ax plus b. How we're getting that is we're using a u substitution. Let u be the denominator. du is a dx, right? So you're going to have 1 over a coming outside the new integral involving u. And when you integrate 1 over u, you got the ln of the absolute value of u. u is ax plus b. Okay, so 1 over a times ln of the absolute value of ax plus b, and then plus a constant. Another integral that you're going to need to know is this one. Okay, so when you integrate 1 divided by x squared plus a squared, that's 1 over a times tangent inverse of x over a plus a constant. Okay, how we're getting that? So if I were to let y be 1 over a times tangent inverse of x over a, well, then if I multiply both sides by a, and then I take tangent of both sides, tangent of a times y equals x over a. Okay? And then we're going to differentiate both sides. Okay? So I'm going to use implicit differentiation, right? Because this equation here is not solved for y. So the derivative of tangent of a times y is secant squared a times y times the derivative of ay is a, and then times dy dx. Always tack on a dy dx whenever you differentiate anything involving y. Okay, that's something from Calc 1 in section 3.5 when we talk about implicit differentiation. We must have that. And then I just differentiate x as usual. Okay, so the derivative of 1 over a times x is 1 over a. Now, dy dx is the derivative, right? So I'm going to divide both sides by a times secant squared a times y. I've already got an a in the denominator. Secant squared a times y, that's the same as 1 plus tangent squared a times y. Okay? But tangent squared a times y, well, that's the same as, let's see, tangent of a times y, that's x over a, so it'd be x squared over a squared. And then if I distribute the a squared there in those two terms, the a squareds will cancel here on the second term. You get 1 divided by x squared plus a squared, okay? So basically, I showed you that the derivative of this guy is this guy. Okay, and again, these two integrals, definitely memorize these. You'll need these all over the place. Okay. Now, when we talk about partial fractions, the idea is to split an integral that's fairly difficult to integrate into something that's easier to integrate. Okay. So suppose I had 3 divided by x minus 2 minus 1 divided by x plus 4. Okay, well, if I get a common denominator of x minus 2 times x plus 4, I'm going to cross multiply here. I got 3 times x plus 4, that would be 3x plus 12, minus x minus 2, distribute the negative, so minus x plus 2, and then combine the like terms, so 3x minus x is 2x, 12 plus 2 is 14. When I FOIL out the denominator there, I get x squared plus 2x minus 8. Okay, now what if I were going to integrate 2x plus 14 over x squared plus 2x minus 8? Well, that would be fairly difficult to integrate. Right? I can't use a u substitution. The only option that I'd consider here is to let u be the denominator. If u is x squared plus 2x minus 8, du would be 2x plus 2. I don't have a plus 2 in the numerator, right? So that's not going to work. Now, so but I know that these two things are equal, okay? So 2x plus 14 divided by x squared plus 2x minus 8, that's the same thing as 3 divided by x minus 2 minus 1 divided by x plus 4. Okay, and the reason I did that is because now this integral here, which is fairly difficult to integrate, just a u substitution won't work, splits up into these partial fractions. And now I've got something that I can get my hands on. Okay, I can split this into two integrals, and these are going to be this guy right here. Okay, the 3 is a constant, so bring that up front. So you got 3 times the ln of the absolute value of x minus 2 minus the ln of the absolute value of x plus 4 plus a constant. Done. Okay, so that's the value of this integral also. Okay, so the idea here is we're gonna learn how to split this guy up to this guy. Okay, there's a kind of a 5-step process here that we'll follow. Decomposition of f of x equals p of x divided by q of x into partial fractions. P of x and q of x are polynomials. Okay. Step 1, so if the degree of the top, the largest power of x, is bigger than the degree of the denominator, q of x, you're going to divide first to get a function in the form s of x plus r of x divided by q of x. Okay, don't forget about step 1. Students sometimes forget about step 1, and that can lead to a problem for some of the problems that we'll have along the way here. Okay, so that's the first thing that I'm looking for whenever I'm considering using partial fractions is the degree of the top bigger than the degree of the bottom. Okay. Step 2, you're going to factor the denominator into forms that are either linear forms or quadratic forms. This quadratic here is irreducible, so it means that it doesn't factor further. Okay. So just like what we did here, where we factored the denominator. Okay. Step 3, if q of x factors as a bunch of linear factors, then the partial decomposition setup that you're going to want is where you're going to want a sub 1 divided by the first factor plus a sub 2 divided by the second factor plus a sub 3 divided by the third factor plus etc. A sub 1, a sub 2, a sub 3, etc. up to a sub n. Those are just constants. Okay, so like here 3 would be a sub 1, -1 is a sub 2. Okay. Step 4, if p sub 1 times x plus q sub 1 is repeated r times, then you're going to use this decomposition, where you have a sub 1 divided by p sub 1 times x plus q sub 1 plus a sub 2 divided by p sub 1 times x plus q sub 1 squared plus a sub 3 divided by p sub 1 times x plus q sub 1 cubed plus etc. Okay? So here's an example. Like suppose that you're going to, split apart this fraction here into a bunch of fractions. Well, I'm looking at the denominator. So x is repeated 2 times. X minus 1 is repeated 3 times. Okay? And these are linear factors. I don't have any quadratics. So I'm going to have a over x plus b over x squared. Okay, and then now x minus 1 is repeated 3 times. So I'm going to have, say, plus c divided by x minus 1 plus d divided by x minus 1 squared plus e divided by x minus 1 cubed. Okay, and then so this would be the partial fraction decomposition for this guy here. And so if I were to integrate this guy here, it's the same thing as integrating this guy here. Now, The next thing that I would have to do is I'd have to find A, B, C, D, and E, those numbers, whatever they are. Okay, but this is just getting set up. Okay. Step 5 says if q of x, the denominator, has a factor of, that's a quadratic factor, ax squared plus bx plus c, then r of x divided by q of x will have a term of the form ax plus b divided by ax squared plus bx plus c. Okay, so the point of that is to say that whenever you have a quadratic factor here, in the numerator you're going to have an ax plus b term. Okay, don't just write a or b or whatever. Okay, here's two examples. So what if I were to split this up into partial fractions? Okay, well I got a linear factor, x minus 2, and then a quadratic factor, x squared plus 1, and then another quadratic factor, x squared plus 4. None of these repeat. Okay. Also, these quadratic factors here, x squared plus 1 and x squared plus 4, those are irreducible. So it's not going to factor further. So to describe the partial fraction decomposition, I'd say a divided by x minus 2, that's the first factor, divided by, now x squared plus 1, that's a quadratic. So I'm going to need a bx plus c term in the numerator divided by x squared plus 1. Just use different letters, okay? Because the next thing you're going to have to do is you're going to have to find a, b, c, d, all those letters, okay? And then x squared plus 4, that's another quadratic. So in the numerator, you're going to have dx plus e, okay? This would be the partial fraction setup that we would have for this guy here. Now again, the next thing that we'd have to do is we'd have to find A, B, C, D, and E to then go to the next step in the problem. Okay. Here's another example. So like, what if we were going to integrate x cubed minus 2x divided by x squared plus x plus 1 times x squared plus 5 squared. Okay, so I got a couple of quadratic factors here. Now x squared plus 5, that's a quadratic, and it repeats 2 times. X squared plus x plus 1, that's also quadratic, and it does not reduce. Okay, now because all these are quadratics, in the numerator here, I'm going to have a linear factor. Okay, so when I start writing this out, I'm going to have ax plus b divided by the first quadratic, x squared plus x plus 1, plus x squared plus 5, so that repeats 2 times, So I'm going to say it's cx plus d divided by x squared plus 5, and then because that repeats, I'm going to have to need another fraction tacked onto that. And I'm going to say plus ex plus f divided by x squared plus 5 squared. Okay, now the next thing that I have to do is I would have to find A, B, C, D, E, and F. Okay, but this is the beginning of the problem. Like if I were going to integrate this guy here, this would be the way to start. Okay. Okay, when we go ahead and stop right there.